Here we'll discuss hypothesis testing. So, techniques of hypothesis testing can seem kind of odd, confusing. The most important thing that I want you to take away from this is that it's actually pretty straightforward. The complications come from all the formalism that we put on top of it. Now, those complications are ultimately necessary. I don't want to say they're unnecessary or pointless. No. Hypothesis testing is very powerful, but some of that power comes from this kind of stilted, unnatural language around it. These are genuinely questions that people ask all the time. Just example, I overheard students in the hallway, one asking the other a question. Well, if there's nothing going on between you, then why is she on your phone so much? That's a basic sort of hypothesis test right there. If there's nothing there, then why do we observe these things that we observe? One of the basic questions of hypothesis testing is, how likely is it that I'm being fooled? That I'm imagining there's some pattern there which is actually not truly there. We've all been fooled by seeing patterns in randomness. People are into astrology because they believe that some random pattern of stars in the sky has some influence on their life. As scientists, we understand the stars are just randomly scattered into what we see as patterns. Our little ape brains, from millions of years of evolution, have gotten good at seeing patterns in the world, even when there's nothing actually there. It's easiest for us to be fooled. So we start by asking, well, what would I expect to see if there were nothing there, if there were really no pattern, just randomness? If conventional wisdom were true, or if there really no difference, well, that's what we call the null hypothesis. We ponder the question, what would I see if the null hypothesis were true? In the example we're doing in the lab, the experiment, I've asked you to mess around with dice and try to modify them to get the 6 to come up more often. The null hypothesis is that the dice is fair and each side has equal probability. Now we know that in real life, I might roll a dice, get 6 on the first time. That's a 1 in 6 chance. I can roll the dice twice in a row, get a 6 both times. Can figure out there's a 1 in 36 chance of that. It's not impossible. It's not even all that unlikely. We could certainly see it if we're playing a game where players roll the dice many times. To start to formalize the hypothesis testing, I want to get a sense of the question. If I roll a dice 20 times, how many times might a 6 come up? Even if the dice were completely fair. That's if the conventional wisdom were true, if nothing had been done to these dice to alter them. So that's what we call the null hypothesis, H0. We contrast that with the alternative hypothesis, HA, the likelihood that I'm going to be fooled then. That's the p-value. Later we'll talk about problems with people putting too much faith in p-values, but the idea is good even if sometimes overdone. Before we look at the evidence, we start with the question, how low does the p-value have to be for me to reject the null hypothesis? How much evidence do I need to make a decision? There are a lot of details. We don't actually accept the alternative hypothesis. Either we do not reject or we do reject the null hypothesis. Now, it's the difference between saying, okay, the null hypothesis looks false, there might be some kind of pattern, versus saying, and I know exactly what that new pattern is. It's intuitive to understand why we'd ask, how much evidence do I need to make a decision? To decide I'm not being fooled, there's something there. By convention, and really nothing more, but in so many studies in economics, we use 5%, sometimes 1%. That gives a boundary. So if the p-value is less than 5%, then people would typically say we reject the null hypothesis. Then if the p-value is greater than 5%, we would say we do not reject the null hypothesis. Again, not the same as saying we accept the null hypothesis. It may be, and in fact often is the case, there's some evidence against the null hypothesis, but I'm not 95% certain that I'm not being fooled. I'm not very confident that the null hypothesis is wrong. We can often end up in these borderline cases. There's some evidence, but it's not really strong. Sometimes that may be that there's just not enough data. If I'm running an experiment, I can do it again, or I can wait till I get more data. There are plenty of cases where people say, I just can't be sure yet. So let's take a normal example. Normal. Often we form a hypothesis test about a mean. Although we can test any value of the mean without loss of generality, we'll often test against the null hypothesis the mean is 0. Commonly, the null hypothesis is, well, there's nothing there. We would say the null hypothesis is the mean is 0. H naught is the value mu equals 0 versus HA, the alternative hypothesis, mu is not 0. Now recognize that we're comparing two very different hypotheses there. The null hypothesis is focused on a point. Mu is exactly precisely equal to 0. Whereas the alternative hypothesis is that mu is something else. I don't know what else. Could be anything. Any real number, just not 0. So those are very different kinds of hypotheses. We should remind you that we're not saying we accept one or the other. We might be able to reject the claim that mu is 0, but even if it's not 0, we might not have a good answer for what it actually is. Anyway, when we look at a sample average under the null hypothesis, the sample average is typically distributed normally. There are cases where not, but those are weird. Typically it is. The central limit theorem tells us that under pretty broad conditions, the sample mean is going to have a normal distribution, mean mu, standard error, that we can estimate from the data. Under the null hypothesis, the mean would have a normal distribution. Now, for small samples, we have to correct for the fact that we're estimating the standard error. We'll come back to that later, talk about the t-distribution. But for now, take it as a decent approximation. The sample average is going to have our usual bell-shaped normal distribution around the true value under the null hypothesis. That's part of why the normal distribution is called normal. It's so common. If I divide my estimate of the mean, x, by its standard error, then the ratio is going to have a standard normal distribution. Under the null hypothesis, it's going to have a mean of 0 and a standard error of 1. Now, suppose I calculate x bar over the standard error to be 1. If I then ask, is that a big difference? Is that a big number? In this null hypothesis formulation, we say that if the true value of mu were actually 0, what's the probability we could observe a value of 1 or farther than that from 0? So in the little picture there, what is the probability that we're in that purple area of the bell-shaped graph, not the middle? In calculating those areas, we find the p-value, because the p-value is going to be that purple area. That's the probability that I could observe a value as extreme as or even farther. That's how we calculate it. We calculate the area under the curve, and that's why it's very important for you statisticians to learn how to do it. It's one of the basic things that we do over and over again. Now we can set different levels of the test, but a common version would say we reject the null hypothesis of mu equals 0 at the 5% level if the p-value is less than 5%. We can look at the area and say that's the same as, once I calculate x bar over the standard error, if that's greater in absolute value than 1.96, then I'm going to reject the null hypothesis that mu is 0. Or do not reject if that ratio x bar over the standard error is less than that, 1.96. We often approximate that 1.96 to just twice the standard error. 1.96 is awfully close to 2. That gives us a confidence interval. If the null hypothesis is true, then I would expect to see certain values of x bar, and if that confidence interval includes 0, then I would not reject the null hypothesis. If the confidence interval does not include 0, then I could reject the null hypothesis. The p-value is the smallest probability that would still reject the null, so you can calculate that. For instance, if somebody reports a p-value of 4%, then, all right, I could say, okay, that's less than 5%, so I would reject. Now, I mean, don't take all this without many complications and subtleties. We'll keep on getting back to those throughout the course, but it's worth starting with the simple version.